In this video, we're going to work another example here in drawing a free body diagram and setting up our equations of equilibrium. So here we see a box sitting on the surface, and as indicated in the previous video, we typically don't draw the external contact, but I like to draw at least a shadow or silhouette of the external contact to give us context to helping us guide to the drawing of the free body diagram. So before we start, we put our coordinate system on our document here, indicating that we have positive x to the right, positive y upwards, and counterclockwise rotations are positive. So when I look at this system, first thing I notice is that I have a force that is acting through the center of mass, and that force I'm going to label as W for the weight. I could have drawn this where the tail has a point of application at the center of mass and draw it downward, but I drew it this way just to give me more room in the rest of my diagram. And Newton's third law of action-reaction tells us that we have a force that's going to act in the opposite direction of equal magnitude, and I'm going to label that force coming from the ground, or the ground reaction force, and that's applied in line with the weight vector. We have a force coming from the left onto the box, and I'm just going to label that F push. A force on the opposite side applied to the box has a point of application, and going to the right that acts to pull the box, and I'm going to label that F pull. And then there's one more force to indicate here that is due to the nature of the contact between the box and the surface, and that's the friction force. And I'm drawing the friction force in the opposite direction to F push and F pull. So the direction of F friction as I've drawn it seems intuitive to counteract push and pull, but once again, as we saw in the previous video, I'm guessing it's this way, but then when we work through our calculations will confirm if my guess is correct. So now that we have our free body diagram set up, we're ready to move forward with our equations of equilibrium. And we always start with the expression of Newton's second law, or rather the special case of Newton's second law, where acceleration is 0 in the x direction. So I'm going to go and find all the x directed forces. So I go back up to my free body diagram. I start on the left, and I start working my way from left to right, and every time I encounter a vector that's perfectly horizontal or aligned with x, I'm going to include it in my equation. So I have F push, and the direction is interpreted with respect to my coordinate system I had drawn at the very beginning. So this would be a positive a positive force. I keep working from left to right. I skip over the vertical forces. I ignore those for now. And now I come across two more x-directed forces. I have F pull in the positive direction, and I drew F friction going in the negative direction. So I'm just going to take these three labels, and I'm going to translate them or transmit them to my expression, into my first equation of equilibrium. So I'm going to move the 0 to the left hand side, and I'm just going to write down F push plus F pull plus negative F friction. Once again, the friction was a guess. It seems intuitive, but I'm going to guess that it's going to be in the opposite direction. Because this example doesn't have any numerical values, then we just stop right here and we leave it as such, and this is our expression for our first equation of equilibrium. We now move to the y direction. So once again, I go back up to my free body diagram. I start on the left hand side, and I work my way until I encounter y-directed forces, and right away I see I have a W and an FGRF. My W is headed in the negative direction, while the F of the ground reaction is going in the positive direction. And so once again, I move my 0 to the left-hand side, and this equals negative W plus the ground reaction force. So just a couple of more points here. Why is there no moment equation as we saw in the previous diagram? And the reason is because of the nature of the external contact. This is a flat surface and doesn't provide any means for rotation of the box. So in other words, because there's no rotation, all the forces imposed on the box will tend to induce translations. This does not include the application of a force that would tend to tip the box, which could happen. We don't consider those in this type of analysis, so we're only going to consider translatory types of motions. So this ends this video on the second example for a static analysis.